So this beautiful equation is the workhorse for most of deep reinforcement learning. What it says is the value of being in a state and taking an action is the expectation over all possible successor states and actions, the immediate reward that you get for a one-step transition, plus the discounted value of whatever that next state might be. And so you can see this sort of depends on itself. And what that means is we're going to be able to use this as a learning signal where we try to estimate this Q value. So by the way, so now let's think of, oh, and so, sorry, so just to say this very formally, this is the Q value of being in a particular state, particular action with a particular policy. The definition is I'm in the state, I take the action, and then I follow pi forevermore. Okay, so let's suppose I hand you a Q value. How do you use a Q value to generate a policy? Why don't you talk to your neighbors? Take 30 seconds. See if you can tell me how to use a Q value to generate a policy. Go ahead. How do you use a Q value? I'm sorry, a Q function. I give you a Q function. Okay, fully trained, whatever, you can evaluate it. How do you use it to generate a policy?
Yeah, because if you know, because the Q factors in the future states as well.
So in all possible next states, you just really take the highest Q value.
Yeah, because like, the Q value is saying like this is the value of this action. So like in the paternity, this is the immediate.
Okay, 30 seconds are up.
How do you do that for something like
Set 30 seconds. So what is it? How do you do it?
Well, so
You pick your state
Q-
and then you choose the action which
the Q.
Okay, so can you say that more mathematically?
you select argmax Q values.
Nice. So my policy at state S is the argmax, something like this? Is that what you meant? Yes. Good, that's right. So my policy is you give me a state, and I'm going to take my Q function, and I'm going to plug in whatever S you gave me, and then I'm going to somehow maximize over action, and whichever thing that is, that's going to give me that's sort of the best possible thing that I could do. Good. Okay. There are many Q functions and value functions. Why? For a particular domain.
A lot of problems are under determinism.
No.
You have to have a cost function.
So the domain. So let's say we're talking about a domain. Say Go. So the state space is defined. The reward function is defined. But there's many different value functions and there's many different Q functions. Why? Policy. They're policy dependent. Okay. So, however, there's only one optimal policy. And that optimal policy induces what's called an optimal value function or an optimal Q function. Okay, that's typically denoted Q star. So Q star is the max over all possible policies of the Q of that particular state and particular action. It turns out that is also equal to, we'll call that Q pi star. Okay? And once you have Q star, so you can somehow learn or get Q star, then not only are you acting optimally with respect to what you know with your value function, but you are acting optimally. You are acting, you're doing the thing that is, there's nothing better that you could possibly do. Because you will be maximizing, what are you maximizing? Future reward. You're like doing whatever it takes to maximize, to absolutely maximize your future reward. And let's see, we'll finish this slide and we'll be done. Yeah, I mean, this is just the math of that. So what we'd like to do is we'd like to somehow like maximize over the future at every time step. And it turns out that is just the maximum of Q star. But this can also be decomposed into a Bellman equation. So the optimal Q function obeys the idea that there's an expectation over states, an immediate reward, and then a max over the optimal value function. So if we have this thing, we could act optimally. And we're going to use this recurrence relation to try to learn this thing. And that is reinforcement learning. Okay, fantastic. We'll see you on Wednesday, and we'll continue this discussion.